Now let me try to wrap all of this up together and show you how these thoughts are now relevant today as the community is trying to pursue quantum simulations as a realistic application of near-term quantum computers. And this application is with respect to quantum chemistry by and large. And it takes us back to this picture that I gave you at the beginning of nitrogen fixation and nitrogenase. So the perspective I want to give you is one which crosses between the canonical picture of quantum simulations I just gave you and a evolving, emerging, different approach to quantum simulations, which I will describe, called the variational quantum eigensolver. Okay, and here's the challenge. You are given a certain Hamiltonian. And you want to simulate the dynamics of that Hamiltonian with a bounded amount of error, taking into account all those resource constraints that we just illustrated with Grover's algorithm. And you won't be able to simulate the full Hamiltonian. You'll only be able to simulate pieces of it one at a time. And yet you'd like the dynamics to be equal to that of the full Hamiltonian. So let's consider exactly that, a full Hamiltonian, and start to discuss the process by which you would simulate it. So let's go back to the Hamiltonian, which we described at the start of this with quantum chemistry. I said that you had the kinetic energy of the nuclei, and I wanted you to know how easy it is to write down all these Hamiltonian terms. This is freshman year physics in many ways. So the nuclei have a free particle momentum, so that's p squared over 2m. So here we'll write it down in terms of derivatives, three-dimensional derivatives, using notation which is common in the quantum chemistry world. So that's p squared over 2m sub k. So this will be the capital R will be the location of the nuclei. This is the mass of the nuclei. We also have the same kind of term for the electrons. With the mass of the electron involved. And then we have potential terms. For example, nuclei interacting with nuclei. And these potential terms are due to the charge of interaction between them. So two positive charges interacting together. And we'll have a structure that looks like this. A Coulomb interaction, Z1. Z is now charged, not the Pauli Z matrix. Zi, Zj, divided by the distance between the two nuclei, Ri, Rj, together with all the usual 4 pi epsilon knots that I'm leaving out. Then the nuclei electron interaction. Now the sign flips back. We have Zi. The electron is unit charge, Ri minus Rj. And then electron. So here we have unit charge, again, Ri minus Rj. Done. That's it. This is a straightforward Hamiltonian to write down. It governs any molecule. I ought to be able to write it down for nitrogenase. Now, nitrogenase, it turns out, if you wrote this down with the some 5,000 carbon atoms involved, with the number of energy levels that you have for each one of those carbon atoms, maybe 20 to 50, okay, it's inaccessible. You can't possibly simulate such a large system. So the very first step people do in this is to simplify and turn it into just the relevant set of basis states that are involved in the chemical reaction. And if we do that by simplifying, you end up getting another kind of Hamiltonian, First, people normally go into what is called second quantized form. And I won't describe it here, but it's basically simulating, rewriting this Hamiltonian as a number of harmonic oscillators that are interacting with a certain set of statistical guarantees. For example, H, P, Q, A dagger P, A sub Q, where these are raising and lowering operators for a harmonic oscillator in modes P and Q. And there will be some interaction term, H, P, Q, R, S, A dagger P, A dagger Q, A, R, A, S. Maybe you'll commute these in various ways. So these are the individual particle excitations, and these are interactions between the particle excitations to lowest order. And then after this, at this point, for example, with the nitrogenase example, using an appropriately simplified set of basis states, which is almost all of what quantum chemistry is about, you can perhaps simplify this to on the order of 100 qubits in the space. So we're now looking at a Hilbert space of about 2 to the 100. You can't do that with any normal classical computer today. Yet I would like to find the ground state of this system, which has dynamics happening in a 2 to the 100 size Hilbert space. Now, there are two pathways forward from this point that the community has taken, and I want you to know this by way of perspective.